Hey, thanks everyone for joining today. I'm Conor Walker, a final year PhD student in the Gorman Group at ECCB, and today I'm going to talk about how we've been using convolutional neural networks to detect selection in multiple sequence alignments. So for some background on this problem, the aim when trying to detect positive selection between species is to identify if an alignment of protein coding sequences evolve with some sites undergoing selective pressure. This is usually measured using the non-synonymous to synonymous substitution ratio, which is denoted DNDS or omega. And typically an omega value of greater than 1 is interpreted as indicating that a particular site was subject to adaptive selection. And this is usually evaluated using tools such as PAML, which uses likelihood-based tests to identify the presence of positive selection. And these tests assume multiple site classes and compare the likelihood that an alignment evolved with high omega at one set of sites to the likelihood of no sites having large omega values. And this can be tested either at the whole gene level, at specific sites, or at specific sites, as well as on specific branches. And so while these tests generally perform well in this task for detecting selection and alignments, a problem has been repeatedly identified in that likelihood-based test accuracy is often confounded by alignment errors and indels, and alignment accuracy is therefore crucial for these methods to perform well. Recently, convolutional neural networks have been very successful when applied to traditional inference problems in population genetics, including detecting selection. And so we were wondering if we could use these methods to address the issue of accuracy in the presence of alignment error when inferring selection in a phylogenetic setting, and so we have sought to find out. And our general approach for investigating this problem has been similar to the workflow one might utilize for evaluating likelihood-based testing. That is, first we generate some data for training, validation, and testing our network using simulated sequence evolution. And these simulations generate so-called true alignments and come with true labels indicating selection or no selection, which corresponds to a low or high omega values at site class 3 for those alignments. And we need a lot of training data for our problem, and a simulation approach means that we can generate as many of these alignment true label pairs as necessary to validate our approach. And so step 2, we align these simulated data using several aligners of interest, although today I'll be focusing on training data aligned using cluster omega, and testing data which has been aligned using multiple algorithms. We then train networks on these alignments, testing a variety of architectures and hyperparameter values. And then finally, we can evaluate the performance of each trained network and explore what they have learned. Now, in likelihood-based methods, we would perform all of these steps except for step 3, the training phase. And while this represents an additional step during the establishment of CNN-based methods that we're exploring, it's a step that could potentially be phased out for an eventual end user if a pre-trained network were to perform well enough across a diverse test set of alignments, although I'm not going to present such a general performance network today. And so moving to step 1 and 2 of our workflow that I just showed, which is generating and aligning our data. And this is achieved by first deciding some set of evolutionary parameters of interest, which represents realistic sequence evolution. And the goal in establishing CNN-based methods is to assess a broad enough range of parameters that it's convincing, but remains manageable within the many degrees of freedom across possible parameter choices which we could use for simulation. And so here I'm showing a set of parameter values, which we use as our so-called baseline parameter values, which I'll refer to throughout the talk, which are similar to those used in papers which have previously assessed the impact of alignment error on test for selection when using likelihood-based tests. And so this includes an 8-tip ultrametric tree with the branches scaled to have lengths of 0.2 substitutions per codon, and they have an indel rate of 0.1 per substitution. And the root sequence length in all simulations is sampled from a gamma distribution, which is based on microbial gene lengths. And for each simulation, we choose one of 2 site class distributions, shown here on these density plots, where omega is on the x-axis. And so for one set of simulations, the third of the 3 site classes, shown here in red, is sampled from a uniform distribution of omega between 0.9 and 1 for neutral or purifying selection simulations, and for the other set, it is sampled from a uniform distribution between 1.5 and 5, which represents evolution under positive selection at sites assigned to site class 3. And if these parameters are different at any point in the remainder of the talk, I will explicitly comment on this. And so we can pass these parameter values to indelible, which generates the true alignments and labels that I mentioned earlier. And each of these true alignments can then be realigned under cluster for training, and additionally under math and prank for testing. And so for each set of parameters of interest, we simulate 1 million alignments for training and validation, 50% of which are simulated under positive selection. So all training is performed on perfectly balanced data sets. And we also simulate a smaller test set under each of these parameter values, consisting of 2,000 alignments, which we evaluate with both our CNNs and PAML, which you'll see whenever I show results of performance later. And now moving on to step 3, which is training our network. And so to train our network, we first encode our alignments as one-hot encoded tensors, which consist of n species rows by m alignment columns and a third dimension of depth 5, along which an indicator value of 0 or 1 is recorded, which corresponds to the nucleotide or gap present at each position in the two-dimensional alignment. And the encoded alignments for each parameter set are then fed to our CNN for training, during which we optimize a binary cross-entropy loss function using ADAM optimization. And while I won't go over all of the architectures and hyperparameters tested today, we end up with a network that has around 2.6 million trainable weights and is similar in form to a network architecture that was used previously for inferring small phylogenetic tree topologies. Of note, though, is that the first convolution operates over all n species rows and over 3 columns. And this means that the concept of a codon is explicitly captured by the network, which is shown here as this small box that is slid over the alignment tensor at the first layer of the network. Now, in the next couple of slides, I'm going to focus on the performance of this network in 2 testing scenarios in which we expect alignment errors, and these are with increasing sequence divergence and with extreme indel rates. And so first, I'm going to demonstrate the performance of our approach by comparing the performance of PAML and CNNs for evaluating 2,000 test alignments from a range of branch lengths simulated under the tree topology shown here, so using our baseline parameter values that I showed earlier. And so in these plots, what I'm showing is the true positive rate and the false positive rate of both approaches when evaluating the same test set with increasing divergence, which is shown along the x-axis. And so here, each color point represents a different PAML aligner combination, and each black point represents a network performance that was trained at each of the respective branch lengths. And so what we can see is that a CNN-based approach achieves higher true positive rates than all of the PAML aligner combinations, except for, at some branch lengths, the PAML clustyle combination. However, the PAML clustyle combination also has these characteristic unacceptably high false positive rates. So this looks good. There are a couple of other things worth noting on these plots. So first is that we're still able to capture at these extreme branch lengths true positive selection alignments, whereas all of the aligner PAML combinations detect none at these branch lengths. Secondly, is that this is ongoing work, and we're still looking at the increase in false positive rate at some specific branch lengths, for example, down here. However, it's not unreasonable to expect some higher false positive rates at these extreme branch lengths while still extracting these high levels of true positives. Nonetheless, if we look at the overall accuracy of our approach, we can conclude that CNNs can indeed outperform PAML in the presence of alignment errors at every branch length we have tested so far. And so now focusing on our second problematic area for likelihood-based testing, we changed the baseline parameters shown earlier to use an indel rate of 0.6 per substitution. And this represents an extreme number of indels per alignment, and it should be problematic really for both methods. And so looking first at the likelihood-based tests, here I'm showing the true and false positive rates at the top and bottom, again, respectively. And the true and false positive rates are both at 1, essentially. So it just PAML classifies everything as having evolved in the selection. And now looking at the performance of CNN for this problem, here I'm showing the performance of a CNN which was trained using the architecture shown earlier. And we observe really a negligible performance improvement. So true positive rates are similar, but the false positive rate is nowhere near under control using this approach. However, our network uses a sigmoid activation function in the final layer, which is typical for binary classification tasks. And essentially this outputs a value of between 0 and 1, and this is typically rounded above 0.5 to correspond to a label of 1, which is positive selection, and rounded below 0.5 to a label of 0, which is not positive selection. And we can increasingly raise this threshold to become more stringent in accepting positive predictions. And so here, what I'm showing is a range of sigmoid threshold values, so using our typical value of 0.5 in black, all the way up to a 0.99 value shown at the bottom in the lighter shade of grey. And what this achieves is that although you see this drastic drop in true positive rate, you also see this drastic drop in false positive rate. And so it's difficult to detect these things accurately still, but it does get the false positive rate somewhat under control while still getting some signal of true positive rates that we can be a bit more confident in. If we want to evaluate this using a more typical performance metric, what we can say is we can achieve appreciably higher accuracy and precision than likelihood-based methods in the presence of large numbers of indel columns. And so this is by no means a perfect solution, but it does showcase an extreme simulation scenario in which we still retain the ability to call some true positives with manageable false positive rates. And so to finish, I'm going to show you how we can look at what our networks have learned in this problem. And so here I'm showing an example simulated true positive cluster alignment, but instead of coloring the columns by nucleotide, as is typical when looking at multiple sequence alignments, I'm showing instead the site class that each alignment position belongs to, where these red sites, for example, correspond to the sites which were simulated with these high values of omega, so subject to adaptive selection. And sites in light grey correspond to gaps. And so evaluating this cluster alignment using likelihood tests in PAML gives us these site-wise omega-2 estimates, where omega-2 corresponds to the omega at site class 3. And we would expect to observe high values of omega to be identified at true site class 3 columns. And the posterior probability that the site evolved under positive selection is also given by PAML. And so here what we can see is that several of the site class 3 columns shown here at these red arrows are indeed captured with a significant posterior probability. For our CNNs, we can instead generate saliency maps, and these show the regions of the input alignment which were most informative for prediction. And interestingly, although we didn't explicitly task the networks with identifying selection at individual sites, we observe this clear signal of high saliency at these site class 3 positions shown here with these black arrows. This means that our network has primarily learned to detect selection using information present at sites simulated under positive selection. And so focusing on another example, these high saliency columns that I was just showing may even provide a mechanism by which positive selection can be identified at individual sites with a lower false positive rate than the equivalent PAML predictions. And so, for example, the previous slide contained no sites that were identified by PAML with a posterior probability of greater than 0.99, which we ideally should observe to be truly confident in our set-wise inference of selection when using PAML. So why can this be problematic? Well, here I'm showing an example in which 3 of the 5 true site class 3 sites were identified by PAML with a posterior probability of at least 0.95, only one of which was identified with a probability of greater than 0.99. In addition, however, if we just look at the sites that evolved under positive selection inferred with a posterior probability of greater than 0.95, there were 5 additional false positive sites observed along the alignment. Now, if we look at what our network sees, the 3 true site class 3 sites are also highly salient under our approach, but the false positive sites inferred by PAML are not highly salient. And so what we think is that this demonstrates CNNs can be extended in the future to accurately detect site-wise selection along input multiple sequence alignments. And so, in summary, although this is ongoing work, we believe that we have shown that CNNs can be used to accurately detect interspecific positive selection in the presence of alignment errors, even when trained on cluster omega alignments. It's also relatively easy to identify how CNNs have aligned to classify alignments by looking at these saliency maps, and we can also aggregate these saliency values across our whole data sets and come up with some nice summary statistics about this. And although we currently need to train a separate network per phylogeny of interest, we're now looking at training across more diverse training datasets involving multiple trees to see if these networks can generalize better. And as a final point, although training of networks is computationally expensive, once trained, a network-based approach is potentially much faster than typical workflow involving expensive alignment algorithms followed by PAML analyses. Additionally, aligning our data using cluster removes a lot of the computational burden imposed by the alignment algorithms required to achieve good performance using PAML, and this makes our approach highly desirable. And so with that, I'd like to thank everyone who's contributed to this project and everyone in the Goldman Group. Thank you all for listening, and I'll be happy to take any questions.